Okay, welcome to class and happy Friday. We're going to get started where we left off last time. But let me first talk about our learning objectives for today. One of the first things we're going to learn how to do today is how do you label a phase diagram if it was blank, right? And what I mean by that is how do you know where there's a single phase region or a two-phase region? Because the very last thing we learned about last class was that when you have a non-unary system, right, you can have like pure syrup, which is one phase, but you can have a second region of your phase diagram, which is both syrup and sugar, so it's two-phase. We're going to figure out how do we label these things, right? We'll identify a number of important reactions called eutectic, peritectic, eutectoid, peritectoid, and there's other ones, right? What do these mean? We'll also talk about things called line compounds, congruent versus incongruent melting, and we should have time to get to the lever rule, and then we might have time to get these other things, okay? So where we left off last time, we were talking about sugar dissolved in water, and we found out that there's a limit to its solubility. There's a limit to its solubility, and if you go beyond that, it's going to phase separate on its own, okay? And then we implied that the same thing can also happen in the solid state, right? And there we changed the name. Instead of talking about liquid solubility, it becomes solid solubility. So maybe turn to a neighbor and talk about, can you think of an example where you've seen solid solubility, where one solid can be dissolved in another one without forming two phases? So turn to a neighbor. What comes to mind? Okay, what do people think? So let me pick on, let's ask Adam, and then we'll go here. So Adam Lundgren, because I just remembered your last name, I'm going to pick on you. Adam, do we know of any instances where one solid is dissolved in another solid? Without a phase change. That's the key thing. Otherwise, it's a two-phase region. I think we could all think of instances where a solid precipitates out, right? You could have a metal that has little precipitates of another phase. But when do you see something dissolved in another? Any ideas? Nope. How about you behind Miranda? Yeah, interesting one there. When you put salt on snow, what it's actually doing is it's lowering. So if we go back to yesterday's class, we said that like this is our melting point, the line between solid and liquid. We said that changing pressure can change where that temperature happens at, where the melting happens at. Now this is a unary phase diagram, but when you add salt to it, now you make it it's a binary, right? It's salt plus water. And by adding salt, you lower the melting point of this, and so it actually becomes liquid again. So in that case, you're dissolving it in the liquid phase, not the solid phase, but you achieve a lowering of the melting point. That's why they put salt on roads, is it melts the solid ice and gives it liquid, which is less slippery. Any instances, though? What did you think in the gray hat? Remind me your name again. Mitch. What do you think? Play-Doh? Yeah, so it looks like you take like some red Play-Doh, mix it with your green Play-Doh, mix it up, and it's like dissolved in it. But in fact, if we zoomed way in on it, you'd actually see Play-Doh is made of different polymer strands, and you'd find that those polymer strands are still probably phase separated, is my thought. I could be wrong about that, but I think that they've still separated. Yeah, Spence?
What about metal alloys?
So metal alloys, yeah. I bring this up because I don't think many people have thought about where you're going to see this happen at. And so it's generally a new concept for people. Metal alloys is where you're going to see it, most obviously, right? So let's do our most simple one. We're going to talk about copper and nickel. And if we go to our phase diagram, our periodic table, and we look at copper and nickel, first off, we see they're right next to each other, right? Element number 28 and 29. If you look at the oxidation states, and this shows their size down here, right? So if it's a +2 nickel ion, it shows how big that ion is. if you were to compare those with copper, you'd find that they're pretty close. Let's see, nickel is like 0.5, this is 0.46 for the same For the same oxidation state, it's 0.55 and 0.57. So really, they're very close in size. They tend to take the same oxidation states. They have the same crystal structure, and that's key word. We haven't learned what crystal structures exactly are yet, but we will soon. But remember, for now, all we can think of that is how the atoms arrange themselves, right? And the fact that these things are so similar, it's unsurprising that these two atoms, these two metals, can be dissolved in one another. So we can actually draw the phase diagram. So let's go ahead and do so. The phase diagram for copper and nickel. First off, we need to know which one melts at a higher temperature, right? Imagine you have pure substances for a minute. If you're going between copper and nickel, let me give myself some more room. So you've got copper right here and nickel over here. Then this would represent your weight percent nickel, right? Going from 0 to 1, or 0 to 100, however you want to do it. I guess since we're doing weight percent, we'll go to 0 to 100, as opposed to fraction, which would be 0 to 1. Okay? Now, copper melts at a temperature of 1085. Plotting temperature on the y-axis for both of these. Nickel melts at a higher temperature. It's up at 1453 Celsius, right? What happens is that at low temperatures in this region, I can go ahead and substitute copper and nickel for one another all the way across, and it's still just one phase. We'll call it just the alpha phase. Alpha because we haven't learned what the actual crystal structure is yet in this class, but we will soon. So for now, we just assign it a Greek letter. We call that the alpha phase. It's a solid. But we know above these points on either side, it's melting, so we're going to have liquid up there. And then you get this interesting two-phase region that looks like this. So up here you've got liquid. In between, in that region, you're going to have a mixture of liquid and solid. And remember, a phase diagram represents the thermodynamical stable phase under equilibrium, right? Equilibrium versus non-equilibrium is something we'll talk about later when we talk about kinetics, right? But this says, like, if you left it there for infinite amount of time, this diagram will tell you what phases are present. And it tells you that you're not just going to have it be solid or liquid. You're going to have icebergs, right, of this metal floating in liquid metal, right? Or it might not float. Actually, it would probably sink, okay? But you're going to have both of those in equilibrium. We need to introduce some vocabulary. These lines have special names. The line along the top we call the liquidus line. And the line along the bottom we call the solidus line. And what happens is that at any given temperature or composition, if we start to cool this down, this is what happens. Let's pick a different color. Let's say you start out with a composition which is about 25% nickel, 75% copper, and you're going to start to cool it down until room temperature. What happens is that the second that it touches that liquidus line, right there, maybe that's at like 1100 or 1200 degrees Celsius, your very first solid starts to form. And the phase diagram tells you what the composition is of that solid. You would draw a flat line all the way over until it touches that point. You would drop a tie line down, and this we're going to write CS. This is C naught. That CS represents the composition of the solid that initially forms. So you're cooling this thing down. When you get to whatever this temperature is at, 1200, 1100, whatever that is, the very first solid that forms is a different composition than what you started with. You started with 25% nickel atoms, 75% copper. But when you first form a solid, it's much more rich in nickel. It's almost the exact opposite, maybe 75% nickel, right? This is because this is how these diagrams work. The phases that exist in a two-phase region, the borders on the left and the right tell you what the composition is of those two phases. Since it's liquid on the left and it's solid on the right, the alpha on the right, that's going to tell you the phase of the composition of those two phases. And then notice this, at any time in between, let's say you cool it down further. So now you've cooled it halfway through this two-phase region. Look what's happened. Your solid has gotten less rich in nickel, right? It's now maybe 50-50. And your liquid has gotten less rich in nickel as well. And your ratio of the two is also changing. We'll teach you how to calculate the ratio by the end of class today, right? We don't quite know how to do that. And then by the time you cool it further, when you get this point, now all of your solid is at the composition you started with. And any liquid you have is basically pure copper at that point, right? Almost. And when you go below that, you're left with pure solid that's the same composition as your initial liquid. This makes sense. It's not like we've gotten rid of atoms of one type or the other. If you started out with a 25-75 mixture, you're going to end with a 25-75 mixture. It's just that as you pass through this two-phase region, it gets a little weird, right? It has to follow these solidus and liquidus lines. Any questions? Somebody surely has a question. In the back. Jordan, is it?
Yeah. If you pull it down fast enough, can you end up getting like pockets in your material that are more concentrated than others?
Yeah, I'm going to pull up a picture for this because it's hard to draw, but we will find a nice picture of it. You get this happening. Where's a good picture? This one's right out of the book, okay? This is what happens. If you cool it down fast, this is what's called non-equilibrium cooling. The red line represents equilibrium, and this is copper-nickel again. This is what we've just been working on, right? Meaning that if you cool it down to this point, you're going to expect exactly that composition. What happens if you cool it down quickly is you're not giving the atoms time to separate, right? The initial liquid in this case is maybe 50-50, but that first solid that forms is much more rich in nickel. And so you're literally forcing nickel atoms to clump together a little bit more, and that means they have to travel. They have to do what we call diffuse, which is move around through your material. And if you don't give them time to do that, then they're not going to be able to. And so you actually you end up bending this plot a little bit, right? There's another effect that takes place, which is called supercooling, which we don't talk about yet, but in chapter 11 we will. And that basically moves this temperature down. And you've seen this, right? And we're going to show a cool demo of this later this semester. If you've ever taken water and you leave it in the fridge, maybe you've taken it out and all of a sudden you see it like turns into slush before your very eyes. Anybody seen this? You'll see it later this semester. It's rad, right? That's supercooling. It means you were technically below the temperature where it should be a solid, but there's a kinetic barrier that stopped it from forming that solid until you jiggle it. You give it a little bit of energy, and then all of a sudden it happens. So you can get a deviation from what you normally expect. So this is beyond what we've covered thus far. The end result of these processes working together is that the start of your sample is going to be rich in nickel, and as it grows outward, it's going to be less and less rich, depending on which way this line's facing, if it's positive or negative sloped. You'll see a gradient in the composition of your solid that's forming, okay? So we will come back to this, but that's to answer your question. Okay, other questions I can answer? Anthony?
So if we're coming down from a liquid, what this graph is saying is that we're going to have, so nickel's got a higher point at which it becomes a solid.
Okay.
And so if we hit to like that 1453 or maybe go a little bit below that, then we're saying that primarily the nickel is going to be making up the solids, but there's going to be still some copper.
Yeah, and the amount of copper you can read by just reading where you're at on this line and then drawing a line down, and that'll tell you how much nickel's there and the rest is copper. Okay? We're going to do more examples of this, so I'm going to keep going. Like we'll do lots more of this. Okay? Now, just because things are soluble, like in this region, you can have a single phase, right? So that means that there's one phase present. It doesn't mean that it looks the exact same. All it means is that the atoms are arranged in the same sort of geometric pattern. And I think we mentioned this in class, right? The students here might be in like a rectangular fashion, whereas a different crystal structure maybe is like hexagonal or triangular or something like that. However, nickel and copper do have slightly different sizes. And so if you put in a bigger atom, what it can do is it can spread these atoms out a little bit. They're going to keep their rectangular formation, but they might flex a little bit, right? And so we have to introduce a term called the lattice parameter. The lattice parameter, think of it like a separation distance between atoms, right? So if we had this arrangement, right, that's say a cubic arrangement, but then I dissolve into this solid, maybe there's atoms located at these corners, right? But then I go ahead and I put some bigger atoms into it, and all of a sudden it looks like this, right? Because I put some bigger atoms into it, and that strained the lattice a little bit. We need a way to talk about that. And so this distance, we're going to call A. That's our lattice parameter. And even though you haven't changed phase, you can change the lattice parameter, right? And in fact, if you were to plot the lattice parameter for copper and nickel, I don't know which one's bigger offhand, but basically, weight percent, as you go from alpha to beta, or A to B atoms, you might see like a linear change all the way across, right? If you were to plot that lattice parameter, as you go all the way over to pure B, you might see a linear change, okay? Where it's just going to change along with your composition change, okay? Now, in this case, this is what we call a complete solid solution. They can be dissolved all the way across. That's not always the case. In fact, in many, many, many cases, it doesn't dissolve all the way across. Maybe copper and nickel are just too different. Like what if you took copper, which is not that big of an atom, but you used lead over here? Lead's a huge atom. So you're probably not going to be able to dissolve a lot of lead in copper because it's too big, but you're probably able to dissolve more copper in lead. It's easier to put a small atom in a big lattice than the other way around. So they're going to have different what we call solubility limits. And solubility limits is just the exact same as our syrup and water thing, right? It's a limit at which you can't keep that same phase. It's going to precipitate out as a second phase. Okay? All right. Let's draw what we call the second most common type of phase diagram is a binary eutectic phase diagram. It looks like this. As you go from pure A to pure B, whatever those are, whatever atoms those might be, plotting either atomic percent of B or weight percent. You can do it either way, and they do it both ways. All as a function of temperature. A diagram that is a binary eutectic might look something like this. It's going to have what's called a eutectic temperature, which is going to be a flat horizontal line. Then you're going to have something maybe like this. Here's your melting point of pure A. This might be your melting point of pure B. And it does this sort of thing, right? It has like this V, this notch in it. So this represents what we call the eutectic composition. C, we'll just call it E for eutectic. So that would be our eutectic composition. So let's go ahead and label this thing, label our different regions. We know at high temperatures, things are going to be molten. So the easiest thing to label is going to be the phases that's liquid. We're going to put liquid up here. And then the key to labeling these diagrams, and I've got some examples on YouTube where you can see more of this, but you label it at a given temperature. So if you draw a flat line at any of these temperatures, it has to go single phase, two phase, single phase, two phase, and it has to alternate like that. You can't get two single phases in a row or two phases in a row. So if liquid, let's say we took this temperature all the way across, at that temperature, this is a single phase region right there because it's pure liquid. There's no solid present, so it's one phase. That means that the two phases to the left and the right must both be two-phase regions. So let's call this liquid plus something, and this is liquid plus something. When you label these things, go ahead and give them Greek letters. It doesn't matter which ones you choose or where you choose to put them. We'll call this one alpha and this one beta, for example. Now we're going to keep on doing our labeling. If this is a two-phase region, what must this one be? It's got to be a single phase. And we know which one it is because we already chose the letter. We said it was L plus alpha in the middle phase, so that it's going to be alpha phase. Same thing on the other side. This one's going to be beta phase, right? And now let's pick a different temperature and do our same rule again. Let's pick this temperature. If we do our 1-2-1-2 rule, we have a single phase region. We have a single phase region. This must be a two-phase region. Okay? So you're going to have alpha plus beta here. Whatever's on the left plus whatever's on the right. And what this phase diagram is telling you is that at different temperatures, the composition will change, right? So if you are at this same composition, which we're calling the eutectic composition for a minute, at this temperature, then the composition of alpha is right here. And if you heat it up, composition of alpha changes. It actually becomes more rich in B. This is generally the case. It's almost always the case that these lines bend outwards with increasing temperature, meaning if you heat something up, it can dissolve more of the other substance. There's exceptions to this, but not generally. This is the more common. Any questions so far? Okay. This eutectic point is an important point. At that point, we have what's called the eutectic reaction, right? So a eutectic reaction is this. First off, it happens at the eutectic temperature, which is this flat line here. And at that temperature, you have liquid transforming to two different solids, right? If I was right here above this, a few degrees above that eutectic, it's pure liquid. If I go a couple degrees below it, thermodynamics says that should be a pure solid. Now, kinetics might slow that down, right? But we're talking about equilibrium right now, assuming it reaches equilibrium. All of a sudden, we went from pure liquid to two different solids. That is called the eutectic reaction, okay? And what's cool about this is that this happens all the way along this flat line. But only at one point does it go from pure liquid to two different solids, only right here. What if we cooled it down to the left? If we cooled it down right there, then imagine what happens. As soon as it touches this point, it's going to form our first solid, alpha, which has that composition, right here. As we continue to cool it down, we're going to form more and more solid. We haven't shown you yet how to calculate how much solid, but we will soon. But there's more and more forming. And right before the eutectic reaction, this black flat line, your solid is now at that composition. And then you have some liquid, which is at that composition, right? You just draw a tie line to the side and find the two solidus and liquidus lines. But the second you cross over this border, all of your liquid that you had left over is going to turn into this two-phase mixture. So the way that we start sketching these things is like this, right? So let's draw a little, running out of colors. Right above this line, if we were to zoom in on this thing, it's going to have floating chunks of alpha, right? And the rest is liquid. And then right below that, if we were looking at this under a microscope somehow, and we could see this thing happening, you're still going to have those chunks that formed before the eutectic reaction, but the rest is going to be the lamellar structure. And we'll talk about the lamellar structure in a minute, okay? So these chunks that formed before we call proeutectic alpha, and then this is lamellar structure, or eutectic structure. Sometimes they call it just the eutectic structure. We'll talk about why it forms these sort of stripy structure in a minute, okay? Any questions so far? Thomas.
First phase you showed didn't have an eutectic reaction.
Yeah, this one up here had no eutectic. This is a complete solid solution. So at no point do you have liquid turning into two different solids, because at no point do you have two different solids. You've got one solid. So you can't have a eutectic reaction there. Good question. Can I clarify further for anybody? Okay, let's keep going. How would this drawing look different if I cooled it down right at the eutectic composition, right here? Maybe turn to a neighbor, how will it look different? Okay, what do we think? In the back is, next to Will, is it Dave? Dave, how will it be different? So let me just change that just a little bit. It will be more uniform in that it's not going to have these pockets of proeutectic solid, but all of this is solid. Once you go below that eutectic reaction, it all turns to alpha plus beta, but you won't have any proeutectic phase because as you cooled it down, At no point did you have a two-phase region. You went from pure liquid to solid, so you don't form either proeutectic alpha or proeutectic beta. Any questions on this? Okay, let's keep going. Okay, all right, let's do some clicker questions on this. All right, the question I have for you is, consider this same type of diagram. If I were to ask you to use Gibbs' phase rule, could you calculate how many degrees of freedom are present at the eutectic point? So let me remind you, if you've forgotten what Gibbs' phase rule is. Gibbs' phase rule says P plus F equals C plus N. P is the number of phases. F is degrees of freedom. What was C and what was N? C is the number of components, right? So number of different types of atoms, essentially. Number of components. In this case, it's 2. We have a binary mixture. And then N is the number of non-compositional variables. Non-comp variables. So previously, in the water example, that was pressure and temperature. But on this diagram, we're only plotting it against temperature. So that's just going to be 1. Okay? So at the eutectic point, how many degrees of freedom do we have? 0, 1, 2, or 3. I'm going to open this one up. Okay, get your answers in. Okay, we're going to wrap this one up. Answer's still trickling in. I'm going to close it now. Okay, people think what? So it's actually 0. Let's look at this, right? So how many phases are present at the eutectic point? So Thomas? Yeah, it's a great question. Let's do this one together. So there are 3 phases, right? At equilibrium, this thing is 3. It's liquid turning into solid and alpha and beta. That happens at that point. Degrees of freedom is what we're going to solve for. This is going to equal 2 components plus 1 variable. So F has to be equal to 0 in this one, right? There's no degrees of freedom. So what that means, and this is to Thomas's question, we can't change anything here. We can't change composition or temperature and keep those 3 phases in their same fraction that they're present, right? So all along this line, you have 3 phases present, but their fraction of the phases will change. And Gibbs' phase rule says not only that the phases stay the same number of phases, but the amounts of each phase stays the same. Okay, we're going to do another one real quick. How about this one? All right, how many degrees of freedom along the solidus line? The solidus line is where again? I can't even reach it, but the solidus line is this thing right there. That's our solid. If you can't see that, I'm talking about, like that's a solidus line, right? Okay? So how many degrees of freedom are there along the solidus line? Okay, get your answers in. Okay, we're going to close the poll. Okay, closing it. Okay, what do people think? You have 1 degree of freedom, right? The math makes it clear to see why there's 1. The only thing we changed over here is this is 2. So 2 plus f is equals 2 plus 1. F has to be 1. What do we mean by this? What this means is that you have 1 degree of freedom. You can change one thing, and the system's going to change the other. So let's say I choose to change temperature. I'm at that point, which is on the solidus line. If I go up in temperature, then the system says you have to move over in composition if you want to have that same equilibrium, right? Or if I moved over in composition, then it's going to tell me I have to go down in temperature to have that same equilibrium, okay? Yeah, Sam?
When we're counting the phases, are we counting the regions that the line or the point is touching, or are we counting like liquid alpha and beta?
Oh, good question. Count the phases themselves, right? So here you've got beta and here you've got beta. That's just one phase, right? So this would be liquid plus beta is still just 2 phases present because beta is the same on both sides. Yeah, Elias?
Liquid plus alpha and liquid plus beta the same phase, just different compositions?
Good question. Is liquid plus alpha and liquid plus beta the same thing, same phase? No, they're different phases. This is an example where, there's lots of different atoms that are so dissimilar from one another, say in their crystal structure, how they come together, that we call them a different phase altogether, right? So this could be, for example, a cubic arrangement of elements, and this could be a hexagonal arrangement. So we give them different phase names, right? They're not the same. They're both solids, but they're different phases.
So then at the eutectic point, why is there not 4, why are we not using 4 phases?
So if we count them, at the eutectic point, we've got liquid above, liquid here, liquid there, so that's just one phase. To the left and right, we've got alpha and alpha. Down below, we've got alpha and alpha. So it's still just 3 phases. Okay? Just 3 phases. Okay? Let's keep going. Any questions on a eutectic binary diagram? Yeah. Okay, let's do another one. How about this one? If I ask you, I think this is our next question, but we'll just do it together. Yeah. So in this bottom region, down here, how many degrees of freedom are there? So let's do this one together. If we look at it, in this bottom region, say I'm right here, right? I've got both alpha and beta, so I've got 2 phases, which tells me I should have 1 degree of freedom. Okay? 1 degree of freedom means that if I go up, it's going to tell me that I have to go left or right. We haven't learned this just yet, but there's something called the lever rule. It basically tells you at any given point, let's say that we're right here. If we were right there, the lever rule lets you calculate not only, if you draw lines to the side, that'll tell you the composition of your 2 phases. But we want to know how much, not just the composition, but how much of these phases. The lever rule says that it's proportional to the length of this line divided by the total line, right? Or for the other phase, it's the length of this line divided by the total line, okay? So imagine this scenario. Like, let's make it dramatic by putting it on the side. If we started out right here, if I did the lever rule, then this section of line is much bigger than this section of the line. And what that means, and we're going to show you mathematically in a second, but that means that there's more beta phase than alpha phase. There's a lot more beta. It might be like, 90% beta, 10% alpha, for example, okay? And we'll calculate it in a minute. Which means if I move up in temperature, let's say with my 1 degree of freedom that I move up in temperature, what if I move it all the way up to right here? Well, now this section of line is much, much larger still, which would mean I've got almost pure beta because it's almost touching this line. So that means that the ratio, the amounts of those 2 phases has changed. So if I want to maintain equilibrium with the same amount, it's going to tell me that I have to scooch over a hair and be right there. That make sense? We're going to do the lever rule and actually calculate this in a second. But does that kind of make sense? Why there's 1 degree of freedom there? Now, where could you have 2 degrees of freedom? How about that if I ask that? So go ahead, get your points on that one. So be answering this question, but if I asked you, actually, so get your answer in and then turn to your neighbor, where in this diagram do you have 2 degrees of freedom? We're going to tie-dye some lab coats?
Oh, yeah. I wish they'd let us die the lab for the department on one.
Who said no?
I don't know.
Josh said no?
Who said it? It just said on the thing.
It
It
just said-
specifically says you cannot die before.
Yeah. Which is
I would do it anyways. Okay, I'm going to close this poll. All right, what do you think? Where in this diagram do we have 2 degrees of freedom? And what does that mean? Anybody have a thought? Ashton, right? Yeah, let's say you're at this point. At that point, you have just beta phase at that composition. Because you have 2 degrees of freedom, that means you can go up in temperature and over, left or right, and you still just have beta phase. It doesn't mean that you have the same composition, but it means that your fraction of the phases hasn't changed. You still, no matter what, in this whole region, you've got 100% beta phase. Okay? Any questions on the eutectic, binary eutectic diagram? Yeah, liquid would be the same. If you were up here in this liquid region, you could move it around and you're always just going to have liquid. The composition will change, the temperature will change, but you still have 100% liquid. Okay? Okay, let's keep moving. Okay, there are other types of reactions, right? We've already talked about the eutectic reaction. That was a liquid transforming to 2 different solids. But you can also have something called the peritectic reaction. A peritectic reaction means you've got 1 solid plus a liquid, and when you cool it down, it forms a different solid. So we could write this alpha plus liquid forms beta, right? So what does this one look like? If we were to draw a diagram, a phase diagram that has this, here's an example. As you go from pure component A to pure component B, let's assume you had something like this. Pure A melts up here. You've got a solubility that maybe looks like that. You've got a flat line. This, that, this, that. If I gave you this and I said, go ahead and label this phase diagram, how do we label it again? What's our rules? The 1, 2, 1, 2, 1, 2 rule, right? So at the very highest temperature, that's where we're going to have liquid, right? That's easy. That's a single phase, okay? As you move left to right, you know that this has to be a 2-phase region, so let's call it liquid plus alpha. So there's our alpha phase. Now, if this is alpha phase, this has to be that's a single phase region. It's supposed to be 2. So let's call that alpha plus beta, which makes this a single phase region. Let's call it beta, right? That makes this beta plus liquid, and we're in good shape, right? This thing should close down there. Where in this diagram is there a peritectic? Where is alpha plus liquid upon cooling down giving you beta? Right there at that point, right? This is our peritectic point. Happens right there. As you cool it down, you have a mixture of liquid plus alpha, and when you go down in temperature, all of a sudden you have 100% solid at a single phase of solid. Okay? That's a peritectic reaction. Okay? So some diagrams have what's called an intermediate compound that forms. So I'd like you to turn to your neighbor and say, why on earth will an intermediate compound... Well, first let's show you what it looks like. Okay, an intermediate compound, take this one, right? As you go from pure A to pure B, you might have, so this is a 2-phase region, this is a 2-phase region, so all of a sudden this line right here, since our rule always works, the 1, 2, 1, 2 rule, if this is 2 and that's 2, this line itself must be what we call a line compound. It means that it's a compound that exists at only one exact formula. You can't deviate to the left or to the right because the structure won't allow it. It only exists at one formula, and that's actually really common. Line compounds are always vertical lines in these phase diagrams. And the rule is this: a line compound has to be a vertical line, but not every vertical line is a line compound, right? That's tricky. So the only way to find them is to do your 1, 2, 1, 2 rule and start labeling this, right? Here, they didn't label this thing as a line compound. I guess they did if you look down there. But the fact that we have two-phase and two-phase tells me that that's a single-phase region, right? So the question is, why did that form? Why didn't we just have solid solubility all the way across, right? Or at least, why didn't we have like miscibility for a while? Miscibility, that means that you can dissolve it in it. But then a region where there's just two phases. This is not just two phases, this is lots of phases now. So why does it form? So turn to a neighbor, why should a line compound form? Or an intermediate compound in general? Correct. Okay, anybody have a thought? This is a little bit tricky. Why should an intermediate compound form, Spencer?
At that point, is there an exact stoichiometric ratio so that it makes a new compound?
Yeah, it's true, but why? You're absolutely right, that's true. But if, like, again, this is pure A and this is pure B, let me ask you this. It's free energy, right? Smart Alex will say because free energy was lowered, and you're absolutely right. Free energy went down, that's why it happened. And free energy depends on two things. If you take away nothing else from this class, right, from the free energy that we learned about, you know that free energy depends on entropy and enthalpy. So let me ask you this. When you form a compound, like a line compound, let's say that like a line compound forms right in the middle of this thing. So you form AB. That means that the atoms are going to arrange themselves in a very specific way in that compound, rather than just being a mixture, which is randomly disordered, right? So when you form AB, you're reducing the entropy of your system, right? And we know that in general, right, for things to happen, entropy gets increased, or at least that's a driving force for it. But in this case, you went from having a random mixture where they can be wherever, and you're forcing them to arrange themselves in maybe like a checkerboard pattern, right? That's increasing your order. You'd think that's not a good thing. So why does it happen? What's our other term? Enthalpy. And in this class, again, enthalpy has to do with the heat involved in these transformations, but the easiest way to think of it for this class is enthalpy has to do with bonding. So it must mean that the reduction in free energy due to the bonding when these things form overcomes entropy, right? Which is kind of a cool thing to think about. That if you have pure A and you have pure B, these things from an entropy standpoint just want to be mixed. But bonding is so much stronger in some cases that it forces them to arrange, maybe in like a checkerboard pattern, the atoms, right? Where enthalpy is dominating, right? So that's one reason why you could say that enthalpy is greater than entropy. And therefore, you get an overall reduction in your free energy by it forming, okay? Okay, so let's consider a eutectic diagram, just like we did before, but now we're going to put a single intermediate compound in the middle. So it might look something like this. You've got pure A, you've got pure B, and if it was a binary like before, it would have looked like this, right? But now we're going to throw a bone in this, and we're going to say it's not that. We've got a line compound in the middle, right? What this does is it creates two eutectics. Okay? So here we formed our intermediate compound, AB. So this is plotting atomic percent B along the x-axis. Okay? If we do our little rule of labeling here, we're like pros at this by now. We start at the top, we say liquid, right? Which means this is all just liquid here, right? You can just write it once, but it's all that region is just liquid. Which means that this is going to be liquid plus, let's call it alpha. This is going to be liquid, let's call it beta. This has to be liquid plus, it must be beta, because there's just that one line separating them, so that's just beta. right? Over here, let's call this liquid plus gamma, which makes this gamma, which makes this gamma plus beta, because this whole line compound, that whole thing is beta, which makes this beta plus something. We'll call that's alpha, so this must be beta plus alpha. Any questions on labeling this thing? Y'all feel like you could do that? You'll do that on the first midterm, right? I have oodles of confidence in you that you can do this. Thomas. So what I always start at the top, because that's where my liquid is. Anything that's touching liquid, I write liquid plus, and then I write a Greek letter. If I notice, like I did here, that I had a liquid plus beta that I'd already done, and on this side, I was about to write liquid plus gamma, that's a problem, because then you've got beta and gamma, but you don't have room for 3 regions there. So you know that beta must be on both sides of this, and that told me this was a line compound. Yeah? Okay, so this alpha region, it extends all the way down. So now I picked a new temperature, and I said if this is a single phase, that's got to be a 2-phase. And I said if I know this is alpha, it's got to be alpha plus, oh, we already decided this is a line compound, so it's alpha plus beta. Now that I know this is a single phase, it's going to be beta plus something, it's whatever that thing is, which we called gamma. So yeah. So Thomas asked a really good question. He said, oh, hold on a minute. What about this? You got a 2-phase and a 2-phase. The 2-1-1-2, like the 1-2-1-2 rule only works horizontally. It does not work vertically. So it's okay to have 2 phases stacked vertically. It's not okay for them to be side by side. Good observation. Yeah, what's your name? Josh.
So there's no region of just entirely beta?
There is, let's say you could zoom in on this thing. It's like an infinitely thin region of pure beta. That's the way to think of it. And the reason why this happens is some structures, maybe it's just the atoms are arranged in such a way that they're extremely intolerant of extra cations or extra anions, so they only allow them, say in like a checkerboard, right? If you had a checkerboard of red and black squares, where would you put an extra black square without ticking off the red squares, right? You're going to cause a problem. That's basically like a line compound. If you took an extra aluminum atom and you've got a mixture of aluminum and oxygen, like aluminum oxide, there's nowhere you can put an extra aluminum very easily in that structure. So it's a line compound. I think it's a line compound, aluminum oxide. Okay? We're out of time, so let's stop here for today. Enjoy your weekend.